this slide. Okay. I thought I hit this button, but definitely nothing happened. All right, let me just go over a couple of, not many new announcements this week, but let me just hit these. Normally my office hours on Monday, Wednesday are 3:15 to 5:15. And for the rest of this week, it's going to be that way. Okay, in fact, I hope the rest of the term. But today, I've got to be off campus at 3:45. So as soon as I finish my differential equations class, I have to head over to a place my car died completely. I mean, so I'm having to have it towed off. We're going to be getting a new car, and so the salvage place is buying my old vehicle from me, but they're towing it off this afternoon at 3:45. So I have to leave here about 3:30 to get over there by 3:45. I've just got to take my license tag off. We've got to sign over the title, and they give me a check. And so hopefully I won't be off campus very long, but I will be off for, say, 15 to 30 minutes. Hopefully no more than that, okay? May even be less, but I think that's a decent window. All right. Then after that, I don't know of any other interruptions anytime real soon. I know that usually we have a faculty meeting coming up in the month of November, but I think it's a couple weeks off. Hopefully it won't interfere with the class. I can't recall if they've already set the date for it, but I'll be checking on that. Okay. Any questions on anything we've done so far? Okay. Where we left off last time was in Chapter 14, differentiation of several variables, 14.2, limits and continuity in several variables, and this was Theorem 2, which where we're going to pick up now. All right. Now, what if we have a composition of two functions? Remember what that is? If you have two functions, and they're both continuous functions, a composite of two continuous functions is continuous. So let's say f of xy is continuous at a and b, at the point a, b, x equal a, y equal b. And g of u is continuous at some point c, and c is f of ab, okay? So in other words, f is continuous at this point. G is a function of u, and it's continuous at c, which is f at ab. Then the composite function g of f of xy is continuous at ab. Okay? Now, notice, remember when we had single variable calculus, you could do f of g and g of f, and they generally weren't the same. This would be very difficult to go the other way, because g is a function of one variable only. So that variable would be, say, the value of c at f of ab. So you could go the other way, because f is a variable of two functions, and g only has one output. So you can only head this direction in this case, okay? But then g of f of xy is continuous at the point ab, because f of ab is, f is continuous at ab, and g is continuous at that value f of ab, so therefore g is continuous at ab. All right. Now, this is example 5. No, I'm sorry. We should do example 4 first. So let's go back to this and do example 4. It says write h of xy. Let me get my pen activated. H of xy is equal to this. E to the minus x squared plus 2y. Okay, that's some function h is e to the minus x squared plus 2y. All that is the exponent of e. Write that as a composite function and evaluate. So first we're going to write it as a composite function, but then we're going to evaluate this limit. So let's first write that as a composite function. Okay? This is our h, which is similar to the f below, right? The h there is similar to this f here, right? Okay? And we're going to assume it's continuous at the values we're going to be interested in. Well, guess what? The exponential function is continuous everywhere. Okay, so no problem there. Now, we need to write this as a composite function, so we need to come up with a g of u so that we can take g of f of xy. Okay? Almost looks backwards. Yeah. No. That's not quite. We're going to write this as a composite function, whereas g was our composite function before. We need to write h as a composite function. So, so f and h are not similar here. In fact, I don't see anything that would be specifically similar here, except, well, yes, it is. But f and h aren't the parts that are, okay? Forget, so if I said write this as a composite function, what would you do? What would you say it is? What would be the innermost part? Yeah, minus x squared plus 2y. So let that be our f of x here, okay? Let f of xy be this, minus x squared plus 2y. Then my g of u would be e to the u. Okay? Now the h of xy would be g of f of xy, which would be, the g is the e function, your f of xy is minus x squared plus 2y. Okay, that's what they wanted you to do. Write that function as a composite of two functions. The little f is the exponent part, g is the exponential part, and then you do g of f of xy, and you get exactly that. Okay, so that's the first part of it. Okay. It says, now evaluate the limit as xy is approaching 1, 2, 0.12 of h of xy. Okay? Well, what would that be? You just plug it in. You really didn't need to write that as a composite, but we did. They told us to. What would this be? Minus? Say again? Which would be e to the 3. So, I really don't see what the deal was. You could have, yeah, I mean, we wrote it as a composite, but the thing is, all you do is plug it in, plug it in. What I think they wound up saying, well, they did exactly what we did. I don't know why they had us right. Okay, yeah, the first part was the top part and the next part. Now, as occurs for limits of functions of one variable, the most difficult limits are those that are of indeterminate form, okay? So if we want to take the limit of f of xy as xy approaches ab, and plugging ab into f of xy yields you an indeterminate form such as 0 over 0, then you don't know what's happening there, okay? Which is winning, the numerator 0 or the denominator 0, or is it a tie somewhere in between, okay? That's not really a fair way to say it, but it almost turns out that way. Then in some cases the limit exists, and in other cases it does not. We know that if a limit as xy approaches ab of f of xy exists and equals some L, then f of xy tends to L as xy approaches ab along any path, okay? Any path, okay? Now, in the next example, we prove the limit does not exist, okay, by showing that f of xy approaches different limits when 0, 0 is approached along different lines through the origin. We use 3 different methods on the problem to demonstrate a variety of approaches one can take. And this is what the next example is. Now, unfortunately, I've already shown you the answer here. But here's what, this is the function. Let me go on and blow it up here. Okay. All right, here's the function. F of xy is equal to x squared over x squared plus y squared. Okay, now, if you, and what they want you to do with that, there's a function. I'm going to have to reduce it in order to write on it. What they want you to do is evaluate the limit of this function as xy approaches 0, 0. Okay? This function again is x squared over x squared plus y squared. Okay. Now, it says examine that numerically and prove that the limit doesn't exist. It says examine it numerically. Well, of course, if you go to plug it in, which is normally what we do, plug in x0, y0, what do you get? Over, okay, which is indeterminate. It's not 0, it's not infinite. We just don't know what it is, okay? So, what they say to do is let xy approach 0 a couple of different ways. Well, let's start, since I'm over here, from the negative x-axis, okay? And if you, as y equals 0, which on the x-axis y is equal to 0, then that would be 0, and what is that limit? X squared over x squared. 1. That's 1 coming in from the left and 1 coming in from the right. So from 2 directions, that seems like it's going to 1. Well, let's do another. Let's let x approach 0. In other words, come in the y-axis, where x is equal to 0. And what do you have then? 0 over, no, y, whatever y is. But whatever it is, 0 over any number is 0, except, of course, where y is equal to 0. So coming down the y-axis is 0, and coming up the x-axis is 0. So you see, depending on which way you come, you know, along the x-axis the limit would be 1, along the y-axis the limit would be 0. Can't happen. Okay? Now, to make things worse, what if x is equal to y? So this becomes x squared, and this becomes 2x squared, right? And x squared over 2x squared, what's that limit? 1/2, exactly. So at x equal y, you're coming in this diagonal, so it's a 0.5, and up this diagonal is a 0.5. So there you're approaching 0, and it's going toward 0.5. If you approach the negatives, x equals negative y, okay? So this will still be x squared, and this will still be, because if y is negative x, then when you square it, it's still x squared. So that would again be 0.5 coming in those two directions. So here we've got three different limits as x is approaching 0, different limits from 8 different directions, and three different results. Can happen. This does not have a limit as x approaches 0, as xy approaches 0, 0. It just can't happen because you have different values as you come in different paths. And that can't be. Okay. And you can do some others if you wanted to. If you'll notice, approaching 0 from this line here, y is equal to 2x, then your limit is 0.2. This way is 0.2, this way is 0.2, and this way is 0.2. That's not any of the previous ones. Y is equal to 3x, I think you get 0.1, 0.1. Yeah, it's all over the place here. Okay. Coming in this way, it's 0.8, and this way it's 0.8, and this way it's 0.8, and this way it's 0.8. Okay, so there's yet another one, and so you just it doesn't have a limit. That's the point. Okay. Now they show that three different ways. They did along the x and y axis. That doesn't work. If we did any y is equal to mx, which I did 2x and 3x and 1/2x and some of that, we have restricted ourselves to lines through the origin with slope m, and then the limit would be 1 over 1 plus m squared. With different slopes, you get different things, and that's what I showed you before. The third way, convert to polar coordinates, and that's sort of an interesting way. Let's, I guess, do that one. In polar coordinates, just a reminder, hopefully you remember this, your y is equal to sine theta, do we say r sine theta, okay, and x is equal to r cosine theta, okay, for any radius you have, because your sine theta is always opposite over hypotenuse, which is r, and cosine is adjacent over hypotenuse, which is x over r. So that gives you those. So if we convert those, x squared would be r squared cosine squared theta, and y squared would be r squared sine squared theta. Okay, so what you have here is r squared cosine squared theta over r squared cosine squared theta plus r squared sine squared theta. Okay, what's cosine squared times r plus sine squared? Sine squared. 1, exactly. So that'd be r times 1, r squared. So this would be r squared cosine squared theta over r squared. Well, the r squareds go out, and you would have the limit as theta approaches, let's see, that's the problem here, it's r approaching 0, okay, not theta. So this is r approaching 0, Okay? That would be going toward the origin of cosine squared theta. Guess what? Doesn't matter what theta is, if r is going to 0, you've lost your r's. So cosine can be anything between, well, cosine squared will be anything between 0 and 1. Anything between 0 and 1 as r is coming in. And that's really what we saw here. When it's one value here, one there, one there. You know, it's a variety of values, and that has no limit because that can be anything between 0 and 1. Okay. All right. Let's go to example 6. Any questions on that? Those are times when limit doesn't exist. Even though you've got continuous functions and everything else, you have to have the same limit no matter what path you're coming in. So here is one that's not in your text, okay? Let me see what this is. Oh, it is in your text, but it doesn't have this figure in your text. Okay. Or it doesn't quite look like this. It is the same figure. Calculate the limit. Okay, we're going to get to this in a minute. No, that's the one we just did. Oh my goodness, I didn't realize that. Back on the previous pages, the figure for that. I didn't realize they had that figure drawn. And this shows that different limits you go in, as you go in the x-axis, either direction is equal to 1, the y-axis is 0. This is 0.1, 0.3, 0.5, 0.7, 0.9. And by the way, this would be, I think, 0.2, 0.4, 0.6, 0.8. So you can get any value you want it to going in any line that you want to. So it's, yeah, that has no limit. Sorry, I didn't realize this had that figure. Okay. Another thing that's sort of a dead giveaway here is, notice this. For any given xy, okay, not any given xy, but for some value xy, like xy equals 0, 0, look how many, you have a whole string of values that's going to be, here's approaching. Yeah, here it's going to 0, 0.1, 0.2, 0.3, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and you just keep on going, and it's really nuts. So at 0, 0, you don't have a unique solution, you have any of several different solutions. All right, here is example 6, okay. Verifying a limit. Calculate the limit as xy approaches, so I'm going to write it here if I can get my pen. Yeah, there it is. The limit as xy is approaching, I think it's 0, 0, isn't it? Yeah. Of f of xy, where this is your f of xy, xy squared over x squared plus y squared. Okay? Okay. Now this is what it is for any value other than 0, 0. Because obviously 0, 0, again, that's undefined. But this time, is there a limit as xy approaches 0, 0? Well, let's do kind of the same thing we did before. Let's come in which axis you want to do first, x or y? Y. So that'll be where x is equal to 0. So here's your y-axis. If x is equal to 0, this is 0 over y. that's 0, that's 0. 0 divided, that's 0. So all along the y-axis, it's 0. How about let's come in along the x-axis where y is equal to 0. Well, again, the numerator is 0, and this is any value here, so 0 over something is again 0. Okay? That looks okay. Well, let's try, sort of like we did before, let x equal y. Okay? It better come in the same thing. With x is equal to y, what do we get? Okay? When x is equal to y, you get, let's call that x cubed over x squared plus x squared, which would be x cubed over 2x squared, which would be, and as that's going to 0, that's indeterminate. Oh, no. That's also going to 0, okay? Because it would be 0 over 2. So that's going to 0. Well, let's say x equals 2y. Or why not y is equal to 2x? That might be a little easier. It doesn't matter. At y is equal to 2x, then this would be x times 4x squared, because 2x squared would be 4x squared, over x squared plus y squared would be 4x squared. So that would be 4x cubed over 5x squared. And that would be, as x is approaching 0, again you get 0. But let's turn it around and do it the other way. Let x equal to y. And then let's plug in for y's. Well, this will be 2y times 2y, 4y squared. No. Y squared, okay. So, and this will be 4y squared, because x equals 2y, so x squared would be that, plus y squared. So, but again, you get 2y cubed over 5y squared. And that's still, when y is approaching 0, that would be approaching 0. So it sure enough looks like that's approaching 0 no matter where you go. Even though this is undefined at x equals 0, however you do it, you're approaching 0. However you do it, it appears you're approaching 0. Well, let's see if that's indeed what we get. Well, again, they say, let's do that trig substitution and see if it works for that one as well. And remember, what was your trig substitution? Let, and it's always true, x equal r cosine theta, and y is equal to r sine theta. Okay? So what do we have here? The x is r cosine theta times r squared sine squared theta over r squared cosine theta plus r squared sine squared theta. Okay. Well, this would just be r cubed cosine theta sine squared theta over r squared, because cosine squared plus sine squared, left off my square there, is equal to 1. Okay? And, again, the r squareds go out, leaving you r. And as r is approaching 0, this is always approaching 0, because the denominator is 1. The numerator is always something less than or equal to 1. So this is always approaching r. R is equal to 0. So yeah, that does work for every value, x and y, is approaching 0. Okay. Now, let's clear the ink off. Any questions on that one? Okay. Let's clear the ink on that one. Let's see if that's, yeah, that's probably the best one to write on. Here's example 7. It says, determine whether or not the limit exists. Now, we don't have a figure for it, so this is this figure. The limit as xy approaches 0, 0. Okay, like going to the origin here, don't they? Of x squared y over x fourth plus y squared. Whoa! All right. Now, I think if you look at this carefully, my first gut reaction would be, well, since it worked so well last time, let's do the trig substitution. Okay? Let x equal, x is equal to, you don't let it, it is equal to r cosine theta, and y is equal to r sine theta. So x squared would be r squared cosine squared theta. Y squared would be r squared sine squared theta. But you have an x to the fourth. X to the fourth would be r to the fourth cosine fourth theta. Uh-oh, that may be a problem. So let's see what we got. The numerator here would be r squared cosine squared theta times r sine theta divided by r to the fourth cosine fourth theta plus r squared sine squared theta. Okay? The problem here is, with this approach, you have a higher degree of r in the denominator than you do in the numerator. Okay? And what that produces is an r cubed over r to the fourth. That's a 1 over r. And as r is going to infinity, you can't tell what that's going. In fact, that looks like it's going to, r is going to 0. That looks like it's going to infinity. So that's not the best approach on this one. You don't get rid of the theta dependence in the denominator. There's not really a lot you can do. Okay? So they use that separate approach they did, that r is, y is equal to mx. So they don't use this one because you don't get something that's unambiguous there. Whoa! You get something that could be very ambiguous. So this one you won't use that. If you had denominators at the same powers, even powers, yeah, I think you can probably do that, or at least if they're both squared. But this one, no telling. Okay? So here's what they use now. Let y equal mx. Okay, we did this one before. Y is some such. So when m's equal to 0, you're coming in the horizontal axis. When m's greater, you're coming down that thing. You're coming to 0 anywhere. So let's see what happens if you do that. Okay? Well, this will be x squared times mx, right? Y squared is equal to m squared x squared. And this will be x to the fourth plus m squared x squared. Okay? Plus, yeah. Okay? This will be x cubed, mx cubed, divided by x squared times x squared plus m squared. Okay. Well, the x squareds go out, and you're left with the mx over x squared plus m squared. Okay. Now, as x is going to 0, that looks like it's the denominator is going to 0 faster. Well, no, it's not. As x is going to 0, you have 0 in the numerator and m squared in the denominator. So that's going to 0. Okay? Except for m equals 0. So, when you're on the x-axis, let's see, that's the only one that this does not help you with. For any m other than 0, then you get, as x is going to 0, your function is going to 0. But if m's equal to 0, that's along the x-axis, I'm sorry. Y is equal to 0x. So for 0 slope, then you're on the y-axis, okay? So x is equal to 0 there. And you get over y squared. Back to 0, 0. So yeah, for any m other than 0, this is going to 0. For m not equal to 0, this limit is going to 0. Okay? However, this does not mean that all paths through the origin yield the same limit. Consider the path along the parabola y is equal to x squared. Oh, throw that one in here. So here's one we'll say y is equal to x squared. You're coming down along a parabola. So what do you have there? X squared times x squared over x to the fourth plus x to the fourth. Because if y is equal to x squared, y squared would be x to the fourth. This gives you x to the fourth over 2x to the fourth, and this would be 1/2. Okay? That would be the limit coming down the parabola. Oh, no. Okay. Too bad. It's 0 coming every other way. Not every other way, coming in a linear way, but coming in a quadratic way, you don't get that. Now, what does this say to you? To me, you have to be good at guessing. Okay. In reality, I think if you see you have an indeterminate form, you generally say unknown, unless you can show with beyond a shadow of a doubt that no matter which way you go, you're going to do it. And as soon as you came up with as m not equal to 0 is going to 0, But if m is equal to 0, it's indeterminate. If you keep getting that, then I think you have to say, whoa, we can't say anything more. Do you want to do these preliminary questions? That's the end of 14.2. Okay. What is the difference between, well, this is going back to early in this section. Okay. What is the difference between D, PR, and D star, PR? Well, what in the world do we mean by D of PR, D star, PR anyway? What does that nomenclature mean? The book uses the term disk. I think that's pretty good. It's a disk around the point P, okay? And generally it's understood to be the open interval around P. In other words, the disk itself, the boundary of the disk is not included, but anything inside the disk is, okay? The P tells you the center of that disk. The R tells you how far out you go. That's the radius of the disk. So if R is small, it'll be like this. If it's bigger, it's like this. Always centered at the point P. I'll change P and you got other disks. Yeah. Okay. So what's the difference in D at PR and D star at PR? Question. Basically, D is every point within the disk. D star is all the points except P. P may not be defined, but all the others are. So that's the only difference. D is all points within, including P, but D star is all points inside the disk, with the possible exception of P. Okay? Let's make sure that's how they define it in the back. I'm pretty sure it is. This is 14.2, which is going to be on the next page or two. 14.2. D star at P consists of all points on D of PR other than P itself. And funny, in the back of the book they use lowercase p, here they use capital P. Doesn't really matter. Excuse me. Okay, number 2. Suppose that f of xy is continuous at 2, 3. F of xy continuous at the point 2, 3. X equal 2, y equal 3. And that, we're going to assume the first, we're also going to assume that f of 2y is equal to y cubed. Okay? For y not equal 3. Okay? What is the value of f of 2, 3? Okay. Well, if f is continuous at 2, 3, that basically tells you that f of 2y, if that's the value of it everywhere other than x equals, y is equal to 3, it must be that same thing. Otherwise, it wouldn't be continuous at 2, 3. So basically, plug it in, plug it in. That would be, you plug in 3 for y. $27. So f of 2 comma any y, that if f is continuous there, then it must be that value there. So I think it's got to be 27. Let's see what they say. Yep, got to be 27. Now, if you didn't know if it was continuous, you couldn't be able to say that, but since they told you that to begin with. Let's look at 3. I'm sorry? Then it wouldn't have been continuous at 2, 3. Yeah. And you see, they told you it was continuous there, so there's no choice for that to be that. Because if it's that for any other value of y, say y equal 0, that would be 0. For y is equal to 1, that would be 1. For y is equal to 2, it would be 8. And for y is equal to 4, it would be 64. For y equal 2.9, it would be whatever that turns out to be. 3.1, whatever that is. And so you see, for this to be continuous at 2, 3, you can't have a jump there. You can't have a hole there. You have to have it equal to that. Otherwise, it wouldn't have been continuous there. You could have, without this being up there, you could have defined f of 2, 3 to be something else, and it would be continuous everywhere except there. You know, you could have that in this, except at 2, 3, it could have been continuous everywhere in here, but for it to be continuous everywhere, that includes this, so it would have to be continuous at 2. Okay. I don't know if that answers your question, but all right. Number 3, suppose that q of xy is a function such that (1 over q of xy) is continuous for all xy. Okay? Now, which of the following statements are true? A. I'm probably wishing I had written this, erase the other stuff first. Q of xy is continuous for all xy. B. Qxy is continuous for all x, y not equal to 0, 0, and C. Q of xy is not equal to 0, 0. No, it's not equal to 0. Sorry. Thought that can't be right. It's not equal to 0 for all xy. Okay. So, you know that q of xy is a function such that the reciprocal of it is continuous for all xy. Okay? Now, which of the following statements are true? So that indicates that more than one may be true. Maybe all 3 of them. Let's see. Q of xy is continuous for all xy. What's that?
Which one is true?
I can't hear you.
You said which one is true?
Yeah, and it says, which of the following statements are true, which indicates to me that more than one could be true. If it says, which of the following statements is true, that implies only one of them is true. Okay? That Q of xy is continuous for all xy. Now, all we know that 1 over qxy is continuous for all xy. Okay? What's that? It's looking to me like it might be. Let's see, B. Q of xy is continuous for all xy not equal to 0, 0. Okay? What's that? The last one says Q of xy is not equal to 0 for all xy. You know what? That one's got to be true. Because the requirement is this is continuous for all xy. That means Q of xy cannot equal 0, ever. Okay. I don't think B ever has to be true. Okay? It may be true, but it doesn't have to be, I don't think. It says, which of the following statements are true? I know C is true. And I think, therefore, A sort of has to be too, because if QXY was discontinuous, then 1 over QXY would have to be discontinuous as well. So right now my gut feeling is A and C. I feel like C has to be true, but A could be as well. But this says all 3 statements are true. Okay. This one I wasn't sure about. Q of xy is continuous for all xy not equal to 0, 0. Well, if it's continuous for all xy, it would also be continuous for all xy not equal to 0, 0. It just may be it's continuous for 0 to true as well. So yeah, this one would be true too. And this one I knew had to be. All 3 statements would be true. All right, now let's do number 4. Okay, suppose that f of x0 is equal to 3. F of x0 is equal to 3. Okay? For all x not equal to 0. Okay, for all x not equal to 0. And that f of 0y is equal to 5. For all y not equal to 0. Okay? What can you conclude about that's supposed to be conclude, I don't know if you can read that or not, about the limit as xy approaches 0, 0 of f of xy. Okay, well, let's see what this is meaning. Let this be your domain, the xy plane, right? That's where we're viewing from. And f of x0, so any value x, but y is always 0. Y is always 0 on the x-axis, right? So for any value here, if this is x, y, z is coming out this way, f of xy, which would be z, is 3. 3 units out everywhere along here except 0. We don't know what it is there. It's 3 here, 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 here. 3 units out. But f of 0y, so x equals 0 and y is any value, that's 5 units out, coming in like this. Okay? 3 units out here, 5 units out here, So what can you conclude about the limit as f of xy as xy approaches 0, 0? It does not exist, okay? Because if f of x0 is going to 3, f of y0 is going to 5, there ain't no way that limit can be, it can't be 3, it can't be 5, it doesn't exist, okay? The limit doesn't exist. The function may have a value there, but it doesn't exist, okay? I think we're just finished. Let me mark you here. Okay, tag team. One comes in, the other leaves. Okay. Yeah. We're finishing 14.2, and we're just doing the last preliminary question. 14.2, this is 4. And I'm sorry, I'm looking in the wrong thing. 14.2 is the limit does not exist, is what we said on this one. You need to think through it. Now, it has nothing to do with that figure. We just didn't have anything to write on. F of x0, if I just use this as my xy plane, this is already here. Z's coming out this way. Okay? Okay. So f of x0, so any value x, but y is always 0, this is 3 units out here. 1, 2, 3 units out. Everywhere along here, except at 0. We don't know. Okay? But f of 0y, that's x is always 0, but y is any value at all, is 5 units out. So if it's 3 units out there and 5 units out here, what is the limit as x, y approaches 0, 0? It can't possibly exist. Yeah. Because it's 3 coming in here, 5 coming in here, and how are they going to? Yeah, it can't exist. It would be some type of a discontinuity there. All right, homework exercises would be any of the odds 1 through 7. This is in 14.2. This is called limits and continuity of several variables. Any of the odds 9 through 11, or 9 or 11 or both. Any of the odds 13 through 17, either 19 or 21 or both. Do 23, do 25. Any of the odds 27 to 39, and do either 41 or 43 or both. 43, they so it's a picture that I think you can probably figure it out from there. I think it's just talking about values there. Okay. Now, finally, all that, okay, and we finally get to, I think, what this chapter is all about, okay? The main part that it's all about, the fundamental part. All that other was the background. Just like before you learned to differentiate, you went through limits and you went through, doing, and then you learned to differentiate and hardly thought about limits again, right? And when you went to integrate, you thought about Riemann sums and, all that partitioning and stuff, but then when you learned to integrate, you didn't go back and do it again. It just gave you the basis for how you could do it, okay? And for some reason, this isn't coming up. I did this in my last class, too. It came up fine the first time, but then nothing happens when I click on it the second time. Okay, so I think what I have to do is go back here. Well, let's see, is this in play? No, it's not. Okay. Yeah. It opened, but it refused to show. Okay. So let's go from current slide. All right. All right. What we've done so far, all the yak-yak-yakking we've done in the first two sections, we've stressed that a function f of two or more variables does not have a unique rate of change because each variable may be affecting f in different ways. For example, the current I in the function of both voltage and resistance given by Ohm's law, and let's go back and actually do this, that you're pen's taking a long time to set up, that the current as a function of voltage and resistance is equal to V over R. That's Ohm's law in physics. Both of you had physics? Yeah, okay, yeah. Physics 2? Oh, you're in physics 1 now. When you get to physics 2, you'll see this, Ohm's law, okay? If earlier in your career you may have run into it, okay? Now, the current, if the resistance is constant and you increase voltage, the current's going to increase. But if the voltage is fixed and you increase the resistance, the current is going to decrease, okay? So current responds to voltage in one way or to resistance in another way, so you can't always say, oh, it's always this as these are approaching some value. It's which direction you're approaching from, okay? If you're approaching from a fixed voltage, the current as resistance increases, the current would be decreasing. But if you're approaching from a fixed resistance and increasing, then it would be increasing. So you have several things that are going on. Current is increasing as a function of R, V with R fixed, decreasing as a function of R when V is fixed. The partial derivatives are the rates of change with respect to each variable separately. A function f of xy of two variables has two partial derivatives, one with respect to the first one and the other with respect to the second one. And this is, then go back to this. Okay. Here's how we define it. Now, what this means, f sub x is the partial of f with respect to the first variable. Now, the first variable is not a. A is the point, AB is the point at which you're going to evaluate that, but it's with respect to the first variable, x. Okay? So what you do there, you take the limit as some increment is going to 0 along the x-axis, and this is pretty much our definition from before, the limit of f of a plus x, comma b, you're keeping b fixed here, okay, minus f of a divided by h, the difference. So this is change of f with respect to x for change of x. That's what that means. Whereas the partial of f with respect to y is the derivative of y evaluated at the point AB is the limit is k approaching 0 of f of a, which doesn't change, okay, a comma b plus k minus f of a comma b, okay, meaning that you're changing your y by just a little bit, and this is the change of f with respect to y, okay. Now, those two partial derivatives don't have anything in common. F sub x could be increasing while f sub y is decreasing. We saw that in Ohm's law. F sub x could be increasing greatly, and f sub y could be decreasing slowly or increasing slowly. I mean, it really doesn't matter. They can be anything and it's perfectly fine. They're kind of independent of each other. Okay? So that's the first slide, is the beige box in your book. It's almost a literature, isn't it? This f sub x is the derivative of f with respect at xb, some constant b, and f sub y at a b is f sub a, f of a y as a function of y alone. Now, that's the subscript notation, which is the easier one to write. Okay? This is kind of like your prime thing when you're doing single variable calculus. Take the derivative of f with respect to x, you call it f prime. Okay? Here, because you have two variables, you have to somehow differentiate. So this is f sub x and f sub y. If you had 17 variables, f sub x, x sub y, f sub y, you'd have a different sub for every one of those variables. What you do then with f sub x1, f sub x2, f sub x3, up to f sub x17, we're not going to do any of those. Okay. But in Leibniz notation, this is what it would be. The f sub x would be the partial of f with respect to x. Okay? Now notice that's no longer a d. It's I don't know what you call it, sort of a curvy, almost d. Okay? That's the symbol we use for it. That's f sub x. Your f sub y would be the partial derivative of f with respect to y. Okay? As opposed to d's. Okay? They're not d's. They're partials. Okay? Now, if we said to get the same thing we've got here, you'd have to say partial of f with respect to x. That's the f sub x part, evaluated at AB. Okay, I want to make sure they didn't. Okay, that would then plug in this part. And then the partial of f with respect to y, that's the f sub y part, evaluated at AB. Okay. And this would mean the same as that. This would mean the same as that. All right. Now, if z is equal to f of xy, which a lot of times it is, z is equal to f of xy, then we could say partial of z with respect to x, or partial of z with respect to y. How is z changing with a small change of x? How is z changing with a small change of y at that point? Okay? Now, you will also see this. They don't mention it in the book. You could say z sub x and z sub y. You don't have to say f, but most of the time you don't see it that way. Usually the subscript goes with the function, not with the other variable. But you can put the other variable with the partials up there. But I'm not going to say you'll never see it that way, especially say in a physics book or applied math book. They don't care much about the notation. All right. Now, here is the key. Just like we said here, when you're taking the partial of f with respect to x at the point A, B, you're assuming that your y is always at B. It doesn't change. Your x is changing as you're getting closer and closer to A. F of x can be changing, but you're only allowing the x to change. You keep the B fixed. Similar here, f sub y at AB, you would keep the A fixed. You don't change A at all. So you're going to be at the same place here unless you're, same place for x, say here, and then like the y vary as you're coming in to that. That's the key. When you're taking partials of a function that has dependency on two or more variables, you're only taking derivative with respect to one variable at a time, and you treat all the other variables as if they're constants. So leave them alone. Just treat them like they're numbers. Okay? So here's an example. This is example 1. I'm pretty sure we don't have a figure for it. So let's do it here. Okay. Compute the partial derivatives of this, f of xy equal to x squared y to the 5th. Okay? First partial derivatives. First thing you have is partial of f with respect to x. What would you guess that would be? 2x y to the 5th. Exactly. You treat the y to the 5th as if it's a constant, so it would be just treated like 2, left alone, and you just take, well, if x had a coefficient here, it would have been treated just like that. So what's your partial of f with respect to y?
X squared, oh, well, it's actually 5x squared.
5x squared
Y
y to the 4th. You got it. Exactly. Exactly. Partial of f with respect to x, which we could have written as f sub x, is 2xy 5th. And partial of f with respect to y, if you could have written as f sub y would be 5x squared y 4th. Now, this figure goes with the graphical insight. Some of these they call conceptual insight. These are called graphical insights. Okay? I can't get all three on the same slide at once. So let's try this. Here is your function. F of xy, okay, would be this shape here. For any value x and y that you choose down here, there's one and only one value for z. One and only one, okay? Any other x, y, they could be the same, different, doesn't matter, but one and only one value for z. So we can call this the point, come out A on x, B on y, and then f of AB, that's going to be the z value. Okay. Now, the partial derivatives are the slopes of the vertical trace curves. This is why they did all that in 14.1 on trace curves, vertical traces, horizontal traces and stuff. This is it. Because we take there's two vertical trace curves, we're going to take the one where if we're taking the partial of f with respect to x, this is the whole f. With respect to x, we're going to take y's constant at the point at value b, y is equal to b, and then this would be the curve at constant b. This is the sheet. That whole area is the function, but the partial will be the slope at that point along that axis. So this would be the slope right there, along this plane, which is xb, f of xb. In other words, y is equal to b. That's a plane b units away from y, parallel to the y-xz axis. That trace, at y is equal to b, the slope of this curve on that plane, that's going to be f sub x. The slope of that is f sub x at point P, at AB. Okay? And similarly, if you did the partial of f with respect to y at AB, then x is fixed to A. So x equal A, draw a plane there, and then the curve that intersects that plane of the same slope we had here. And you see, if you look at this slope here in the XZ plane, you have to stand back here and look at it. That's a negative slope. As X is increasing, Z is decreasing. But over here, in the YZ plane, okay, actually doing the same thing. As Y is increasing, this is decreasing. Because you're on the downhill side of this one and you're on the downhill side of that. So they're both decreasing. They don't have to be, but they happen in this case to be the case. And at that point, that is the case. But they're sloping different. This is pretty steeply sloping down. This is just gradually sloping down. They don't have to be going in the same direction. If you were back here, this would be increasing here, but still decreasing here. Okay, so they can be doing anything they want to at those things. But this is your meaning of your partial derivative. What is the slope when y is constant at b, or when x is constant? I'm sorry. L sub x is when y is constant at b. L sub y is when x is constant at a. The slope of that line. All right, I think we're ready for example 2. Okay? And this is it. Here's your function. I'm going to blow this up so you can read it. Okay. Calculate g sub x at 1, 3 and g sub y at 1, 3, where g of xy is equal to that. Y squared over 1 plus x squared to the third power. Okay? So we want to calculate the partial of g with respect to x and the partial of g with respect to y. So I'm going to shrink this back down again. And I don't know if you can see that from where you're sitting. Can you? A little. Okay, let me go and write it down. G of xy is equal to y squared. I'm right in front of it. It's hard to see. 1 plus x squared. I was going to say, I don't think that looks like an x there. 1 plus x squared. Squared or cubed? Cubed. Okay. All right. There's your function. And it said to calculate this, g sub x at 1, 3. Okay, my question for you now is, do you plug in the values then take the partial, or do you take the partial then plug in the values?
Take the partial.
Absolutely. If you plug in values right now, you get a constant, take a partial of that, it's 0. No, that gives you wrong answer. Okay. So you take the partial of the function with x's and y's, and then we'll plug in 1, 3 for x, y. Okay? So let's first take the partial with respect to x. Well, I think there's a couple ways you can go about doing this. I prefer this way. I prefer writing this for the first partial as y squared times 1 plus x squared to the minus 3. Okay, now I want to take the partial of that with respect to x. What do you reckon that's going to be? Negative 3y squared.
Don't you supposed to do the chain rule now?
Yes, you do.
Is it inside, outside?
Say again? Yeah, you can put it on the outside. Ultimately, it's going to go on the outside, so if you want to go and take care of that at the same time, you can. And what would that be?
two,
So you'd have a 2x here as well,
yeah,
times
the derivative of the outside. Oh, I'm confused. I forgot how to do the chain rule.
okay. Basically what you're taking is the derivative of this thing with respect to x. Treating the y as if it's a constant. Okay? So the y squared was certainly right there. And then you had a minus 3 times this thing to the minus 4 times the derivative of the inside. Okay? Derivative of the inside is 2x. You're going to put that with this. So it's minus, oops. I erased the 3, but then when I multiplied, I forgot to multiply it by it. Okay? That'd be minus 6. I should have left the 3 in there. Okay. All right. The minus 3 is coming from that coefficient of x, right? And the y squared just stays a constant. But then you got a 2x from the inside. That's what multiplies by the minus 3, making it minus 6x y squared. Okay, that's doing the chain rule and everything else, except for dropping this by power. 1 plus x squared to the
Negative 2. I mean, no, I'm like, yeah. Negative 4.
-4. When you take the derivative, you drop the power. Okay. So if you want to go back and write that the way they did before, that'd be a minus 6xy squared over 1 plus x squared to the 4th power. And then you can plug in the 1, 3. And what does that give you? Minus 6 times 9 over
16.
a little louder.
16.
Yeah, you're right. It's 2. 1 squared is 2. 1 plus 1 is 2.
Yeah.
To the 4th power is 16. Is that what you were doing?
Yes, sir.
All right. So this comes up being 2 will go into that 3 times, 2 will go into that 8 times, minus 27/8. And nothing in common there. Let's make sure they got it right. Minus 27/8 is good for them. Now let's do g sub y, evaluated also at 1, 3. But what do you do first? Yeah, you take partial with respect to y with the variables in it, and then you do otherwise. Okay? Now again, I don't dislike this term here. In fact, well, it doesn't really matter. You can use either one of them. What's that going to give you?
Which one are we using?
Either one. Okay?
I'm going to stick to the one that has negative 3 in it.
Okay.
It'll be 2y times 1 plus a squared to the negative 3.
To the what?
Negative 3.
Yeah, exactly. Which you could go back and write as 2y over 1 plus x squared cubed. Okay? And what would that equal at 1, 3?
6.
6 over,
What we say, 16?
say again? 8, which is 3/4. Exactly. And that's what they got. Good for them. Now, what does that mean? If this indeed is the graph of that, and we're at the point 1, 3, so come 1 over on x, positive 1 on x, positive 3 on y, doing 2. There's 1 on X, 1, 2, 3 on Y. Right. Goodness gracious, it's hard. 1,
Want to blow it up? Make it bigger or?
1, 2, 3. And you go up from here, and there's your point there. And your slope this way is a fairly strong negative. Greater than -3 this way. Have to look at it this way. And your slope this way is sort of hard to see, but the thing is going up here, so that's up 3/4. Less than 1 3/4. All right. And that sure enough gives not a very necessarily a very enlightening graphic here. Let's see if this will make it look any better. I kind of doubt it, but let's see. Okay. They're doing 1 space this way, 1, 2, 3 spaces this way, and then you go up. I don't find that looks like that's in the right place. I would be a little further back this way. And your slope coming down this way is very strongly negative. As you increase X, you're decreasing Z. And going this way, as you're increasing Y, you're increasing Z. So that's why, again, I would never draw this for you anyway. So I'll take it because I don't have to do it. I'm not really all that confident. I agree that they're right on the money there, but maybe they are. Okay. Who am I to say they're not? Okay. These partial derivatives are the slope. Yeah, we said that. Now, we can also use the chain rule. Let's see. There's a little blurb here. Caution. It is not necessary to use the quotient rule to compute the partial derivative in equation 1. We didn't. The denominator does not depend on y, so we treat it as a constant when differentiating with respect to x. But we did have to no, they did it the same way that we did. They rather than doing a quotient rule, they wrote it as a product of a negative exponent. And to me, that's definitely the way to go. All right. So let's go to example 3. I don't think they have a figure for it. And I don't even know where that is. I think that's example, no? Ah, there we go. That was calculating g sub y. Okay. Yeah, I see it now. Except something. No, it's right. All right. That was evaluating the partial with respect to y. And they first did the partial with respect to y and gave you the 2y over whatever the constant x was, and then plugged in the values and got 3/4. Why they didn't show you the harder one, I'm not sure. They showed you the easy one. Okay. So before we get there, let's do example 3. How are we doing on time? Are we out of time? And what time were we supposed to stop? Aren't we 1:55? Why did you let me run over? I'm going to charge you extra. No, I'm just kidding. Okay, so next time we'll pick up. I swear the time just flew by today. Somewhere here I should have a pencil. There it is. Okay, so we'll start with example 3 next time. 14.3. And actually, we'll start with the little paragraph that's before example 3. Started to say it a time or two, but we didn't. All right. Oh, let me give you a few homework exercises here. Okay. I think you can do number 1. Okay. And 3. I think you can do 5, but if 3 variables throws you, you can hold off and we'll wait till we do those. Okay. Not too many there. Most of what we did was in 14.2. All right. Good deal. Any questions? All right. We'll end the slideshow there.